So vibrations within the broader field of classical mechanics is the investigation of oscillations that occur about an equilibrium point. So what that means is for us to have a vibration, we have to have something that is oscillating, get a thinner line, oscillating about an equilibrium point, right? So that's the whole study of vibrations. So vibrations can be desired and undesired, right? So they can be helpful. Say you've got a soil sieve or a rotary sander, and you're trying to filter out soil or trying to sand a component or a piece of wood without leaving scratches in it, or destructive, right? So an aircraft frame and resonance can be very destructive. The oscillations that form a vibrating system can be periodic, like a pendulum, or random, turbulence in an airplane, or a combination of the two. So vibration impacts our daily lives in a number of ways, right? So banjo strings vibrate between 140 and 400 hertz, but the vibrations felt by a passenger car are typically under 6 hertz, right? And so you can use the tools that you learn in this class in your daily engineering life. So maybe you are a seat designer for a car and you're really trying to make a seat more comfortable. Instead of just continuously adding damping or cushions, you could actually look at some of the vibrational characteristics of the seat and see what people are feeling and try to figure out the specific frequencies that you want to dampen out. The consideration of vibrations and their associated mathematical modeling are important factors in the design of a number of mechanical systems. And we're going to try to look at some of the mathematical principles that underline vibration modeling. This builds on two foundational concepts from mathematics. That is going to be differential equations and then Newton's laws of motion. Now, we do need to do a little bit of review for this class, and we'll keep the reviews pretty simple. Review 1.1, Newton's laws of motion. So one, and I'm going to paraphrase these, right? So in an inertial frame of reference, an object either remains at rest or continues to move at a constant speed unless acted on by another force, right? So an object at rest remains at rest an object in motion remains in motion. Second law, in an inertial reference frame, the vector sum of forces F on an object is equal to the mass m that applied by the acceleration of the object. F equals ma, right? And typically the mass here is to be assumed to be constant. So force equals mass times acceleration. And then Newton's third law is when a body exerts force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction of the first body. So a force, let's say a force on a second body exerts, an equal and opposite force. Now, of all these rules, right, laws, they're all important, but in this class, we are going to use force equals mass times acceleration, and that allows us to transition energy in a vibrating system between the force applied on the energy and the acceleration of the energy about a static equilibrium point. In this course, we are going to initially focus on single degrees of freedom. So this is chapter 1.1, single degree of freedom systems. So in its simplest form, the phenomenon of vibration, right, is just an exchange of energy between potential and kinetic energy. Right? So I have potential energy when my spring is completely compressed or completely extended, and all of my energy is stored in the spring and my mass is not vibrating. And then I have kinetic energy when my spring has no extension to it and the mass has a high velocity, typically moving through zero. And so you can look at that on one of these oscillation plots that we've had that goes like this. And I may have a high kinetic energy here and a high potential energy here. And we'll talk about that more as we go through the class, right? And this is time and this is displacement. Okay, so a 1 degree of freedom system could be a lot of things, right? It could be a yo-yo. So maybe you've got a yo-yo and this is your hand and this is you playing with your yo-yo. And the yo-yo is going to move up and down in 1 degree of freedom. We're going to call that system X for the remainder of this course. But it just goes up and down. You could have a pogo stick. And this is you standing on a pogo stick. And the pogo stick is bouncing, right, up and down. And again, you've got X, and you're going to be bouncing on that pogo stick through time. You could have systems that don't just go up and down, that go in one direction, right? So we could have a door, and that door is on a set of hinges connected to a wall. And then this door wants to swing, well, let's use a different color there. This door wants to swing in and out, and we might call that rotational direction of freedom theta. But again, we only have one variable, and that's 1 degree of freedom system. So typically we'll use X and theta, but you could also use Y or Z, and then but we'll use X and theta, and we're typically going to write these as a function of time, because you will have a displacement X as a function of time, right? So the displacement changes through time. And so we have to write those as a function of time. All right, how do we draw these out? We might draw these out in a number of ways. So a very common way is we can do a mass on a spring attached to a fixity. That's your fixity. That's your spring. And that's your mass. We'll label spring with an M and a stiffness with K. And now I have 1 degree of freedom. Do it in blue. Acting up and down. And I'm typically going to say, let's say X is positive facing downwards. Right? Now I could also have a system that rotates. Here I have a fixity. Here I have another fixity. And a fixity is just my edge of the system that's not going to move. I might have a pin moment. I have a massless rod, and then I have a mass at the end. And in this class, we're only going to do point masses. And this rod might be of a length L. And then over here, I have a spring. And now, well, let's draw that dashed. So it would move out here. And my degree of freedom is going to be theta as a function of time. And that's how that system will oscillate. And my spring would still be attached like that, kind of drawn dashed so you know it's the displaced spring. And what you'll notice is that I still have a 90-degree angle here, and that's from the assumption of small displacements, right? So review 1.2. The assumption of small displacement states that the displacement of a system is considered smaller than the initial geometry of the system, right? That means second order effects caused by the displacements within the system are ignored. The second order effects could be loads or angles at the points of linkages, springs, connections, right? So that's the assumption of small displacements. And that's review 1.2. I'm going to put that in blue. All right, and so because of the assumption of small displacements, any change in that angle from 90 degrees to anything else would be a second order effect, right? And because of that, then we assume that that spring still connects to the wall at a 90 degrees, right? And I drew the displacement here pretty exaggerated, but if you had a very small displacement in M, you could see how it would be very hard to even pick out any vertical movement of that spring. But again, the assumption of small displacements means that when you do problems like that, the 90 degrees will stay constant. And then another one, which we won't talk about for a while, is rotation. And we could take a spring. Let's just draw the spring the same way. So we have a reference of understanding that we could draw a spring like this. But instead of, say, taking the degree of freedom to go like that, which is perfectly valid, let's take our degree of freedom to go like theta. And so we might have something that looks like this. And then we would have K, which is our stiffness of the spring, subscript theta to just show it's a rotational theta. And we're trying to spin our mass, right? And if we do that, the value of importance there might not actually be mass. It might be our polar moment of inertia, J, right? Because that's what's going to resist the rotation. So all of these are valid 1 degree of freedom systems that we could talk about through the course of the class. However, the most common system that we will talk about is going to be a little bit more boring. And it's going to be a 1 degree of freedom system that looks like this. We're going to have a fixity on the left. We have our spring that stores our potential energy. And we are going to call that spring K. We have our mass, M. And we are going to displace to the right, X, right? And our mass, our moving mass stores our kinetic energy. Our spring stores our potential energy. I like to draw a series of balls here, just so we know that it's kind of on some sort of bearings and it's a frictionless surface on our fixity, right? You don't have to draw those out, but to me, it just kind of helps to set a frame of reference because as engineers, we like things to be stationed on the ground. This is the system that we are going to consider most commonly as we build up these equations. All right. However, we've drawn this system in a 2-dimensional frame of reference. The mass takes up space. That's not really true. What we're actually going to be solving is what's a point mass that looks like this, and there's going to be two forces acting on it. In this situation, let's say we displace the spring a little bit to the right and the mass is moving to the right, right? So the mass is moving to the right. So we have X positive that way. We're going to have a force acting back. And that's going to be the force of the spring extending and wanting to pull this point mass back. And then because we have a mass moving forward and to the right, Newton's second law tells us that we have a mass times acceleration. Now that force has to equal the mass times acceleration because all of these forces have to balance. So the sum of forces in the X have to balance. But this is how we are going to model these systems, typically as a point mass. All right, I also want to talk about linear springs. So in this course, all we do is linear, right? Everything is linear. And so we need to talk a bit about linear springs as an idea of introducing the conceptual aspects of linearity, right? So when we have a linear system, it doesn't matter how far things displace or what speeds they move at, everything is always going to be governed by the same set of equations. So a mass is linear. It doesn't matter how fast our mass is moving for our systems, it's always going to be the same mass. But the best way to think about this in terms of this class is to look at a spring. And so we typically have a spring that we may draw like this. And then we have some sort of point mass acting down on it. And let's say we have an F equals 0. So we have no force applied to the spring. So the spring is not compressed or the spring is not extended. If I were to draw that in a 2D plot, where this is my deflection, and this is my force, I would be right here at the middle. Now, let's say I wanted to extend this spring some distance x. And so what I'm going to do is have a spring, and I am going to try to, let's see if I can do this, extend this some distance x. So to do that, I have to apply a force acting upwards, and this bottom part here is how tall the spring originally was. And now I have created a spring that for every unit of force I apply to it, I get an equal amount of deflection. And so I can go ahead on this little line here, and I can say that is the spring at this exact location, right? Now I can do the same for a compressed spring. And now I have a force acting down, and this here is my deflection x. So what have I drawn? I have drawn a system that is compressed. Oh, let's stick with our color scheme. I have drawn a system that is compressed. And the compression of that system, right? The compression of that system results in an equal force acting back up from the spring for every amount of displacement I have taken. And this is what's a linear spring. One way to think of it as a linear spring is because we have drawn a linear line. Okay, what would a non-linear spring look like, right? So a non-linear spring might look like something, let's get rid of that, might look something like this. So for a certain region, it behaves mostly linear, but after it deflects enough, it takes a lot more force to extend it, right? So maybe you This is not like a spring and yielding, but maybe you have a specially designed spring where you have a certain amount of the spring that enables it to act relatively passively. And then once you hit enough deflection, you want it to get stiffer. And that's what a nonlinear spring is. And there's lots of different ways you can design nonlinear springs, or springs are linear, or all springs are nonlinear, right? But we can typically model enough springs as linear over enough of their range to make them useful. That brings us to a really good expression, which comes from George E.P. Box, and that's from 1919 to 2013. And he has this famous saying, right? All models are wrong. However, some are useful, but some are useful. And what that means is that for our linear models, our point mass models, these models are wrong. They are not a real representation or the exact representation of a system. However, they are a representation of a system. We can do a lot with linear models, and there's no reason to use nonlinear models when a linear model will suffice, right? It's cheaper and easier to understand, and also easier to explain to others. So in this class, just remember that everything we're going to go over to some extent is wrong, but hopefully a lot of it is very useful.